Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics, and we have been going through the paper on physics of materials, and in this paper we have the chapter on bondings in solids, and in the previous lectures we have been going through the primary bondings, namely the covalent bonding, ionic bonding and metallic bonding, and in this lecture 7 we will be going through the secondary bonding, and the contents of today's lecture are as follows. We will have thermal expansion of metals as at the beginning, followed by the interaction between fluctuating dipoles, permanent dipoles, hydrogen bond and van der Waals bonding. Now, these are the secondary bondings, right. And the first section, namely the thermal expansion. When do you get thermal expansion? When you heat a solid, in general solids expand on heating, and you see the potential energy curve, right. The bond energy or the potential energy as a function of the distance between the two atoms, right. What is this origin? The origin refers to the presence of an atom here. You see an atom here, and there may be another atom somewhere here. You see here an atom, right. So, the atom will be here at T is 0 Kelvin, absolute 0, the atom would have been here. Then you know what happens is they are the vibration energy levels. You know, in solids even at 0 Kelvin the atoms are vibrating. At a higher temperature the thermal energy becomes larger and the vibration amplitude will become larger. You see the vibration amplitude at T 5, a higher temperature is greater than T 1. As the temperature increases, the vibrational amplitude will be increasing. The important point is, even at 0 Kelvin the atoms are vibrating. This is called the 0 point energy, and it was thought at one stage at 0 Kelvin the atoms will be at rest. This is according to Max Planck. He wrote E is equal to NH nu. So, according to Max Planck the atom should be at rest at 0 Kelvin, but according to quantum mechanics, you know, the first problem that you study is the so called harmonic oscillator problem in quantum mechanics, and so according to quantum mechanics the eigenvalue for the atom, the vibration energy levels are given by E n is equal to n plus half into h nu, and so when n is equal to 0 that will be half h nu. Even at 0 Kelvin the atoms will be vibrating, right. These are 0 point oscillations or ZPE, 0 point energy will be even at 0 Kelvin the atoms will be vibrating. As you increase the temperature, what will happen? The vibrational amplitude, it will become much larger. Eventually at one particular temperature, the bond which is operating between these two atoms will be broken, and that is called a melting point, right. That is called a melting point. Now, we are not going to the melting point now. When we heat, what happens is, you have got one atom here, what will happen to the position of the other atom, or the mean position of all the atoms are vibrating. We want to see the mean position of the second atom. So, let us assume that the first atom is at the origin, and this refers to the mean position. You note that the mean position keeps on increasing, right. The mean position goes on shifting towards right. The point is, it is shifting towards right. At 0 Kelvin, the distance that separates the two atoms will be this, right. Okay. You see the distance separating two atoms at 0 Kelvin will be this much. At T1, the distance separating the two atoms becomes much larger. What about T5? At T5, the distance separating the two atoms, one will be at the origin, the other will be here, the distance becomes much larger. Therefore, you should note that as temperature increases, the mean distance that separates the two atoms becomes larger and larger. That is how you are able to explain the thermal expansion. Upon heating, the solids will expand, right. That is the important point. The second point is, when we are talking about bonding and the bonding energy, right, which one has got highest bonding energy, right. Now, you see for instance diamond, then what do you know about diamond? The binding energy of diamond, then tungsten, then maybe aluminum and so on, the binding energies are different, or the melting points are different, right. Now, therefore, if you have a graph of this shape, the potential energy curve looks like this. You compare the potential energy curve which is looking like this, it is deeper. Now, what is 13.6 electron volt? Where do you come across 13.6 electron volt? 13.6 electron volt is the one that you come across in the hydrogen atom. That is the energy with which the electron is bound to the proton in the hydrogen atom. In the hydrogen atom, you got a proton and the electron, the only one electron is there. The binding energy is 13.6 eV, right. Now, if you supply 13.6 eV, then the electron can be removed, right. That is called the binding energy, right. Similarly, so how do you measure binding energy? I told in the first lecture, the cohesive energy is this much. It is called the cohesive energy, that is the height from this point to this point, that is called the binding energy or the cohesive energy, right. And this is called the interatomic separation or interionic separation in the case of ionic solids. This is called the cohesive energy or the binding energy or the bond energy, and you compare these two, right. You compare this one with this one. Now, which one has got the binding energy or which one will have the higher melting point? You call this solid as A, and this is the graph for the solid B. Now, this one has got a deeper potential well, right. The potential well is deeper. Deeper means it is strongly bonded. The binding energy is this much. The height is much larger compared to this height. You see the height here, the height, the binding energy, that is the from this origin, the shape of the curve to this x axis, this is the binding energy, right. This is much lesser compared to the deeper potential energy curve that you have got here, right. The important, and so this the second one B has got a higher melting point, higher bond energy, that means higher melting point. The energy required to break the bond is higher in the second case compared to the first case. So, the point I want to impress upon is the following. There is the thermal expansion and bonding are interconnected. If the bonding is stronger, the potential energy curve will be looking like this. You see the displacement, the displacement at T5, the distance between this and this, right, it has shifted to the right, no doubt, but it is much smaller. When the bonding is stronger, the thermal expansion will be smaller, right. You note this, you see the mean interatomic distance has come from here, this is the mean interatomic distance at 0 Kelvin, but at T5 the mean interatomic distance or the distance separating the two atoms has become much larger. Whereas, in this case T1, T2, T3, T4, T5, you see the distance has not increased so much. That means, in a strongly bonded solid, namely tungsten will have a lower thermal expansion, diamond will have a lower thermal expansion. The melting point is stronger, already the bond is very strong, right. So, when you heat it, the bonding is very strong, therefore, the thermal expansion will be much smaller. Whereas, in a solid like aluminum, which has got a lesser melting point compared to tungsten or diamond, the thermal expansion will be larger. Message that we want to convey, we want to understand from this graph is, when the potential is shallow, the thermal expansion will be larger. Okay. When the potential is deep, as in the case of tungsten, thermal expansion will be weaker. And I told you just now about the harmonic oscillator problem. Now, suppose someone asks a question, why do you study harmonic oscillator? What is the purpose of studying harmonic oscillator in quantum mechanics? The answer will be, where do you find harmonic oscillator in reality? The atoms in solids are the best examples for harmonic oscillators. The atoms are vibrating, right, they are vibrating, but really the vibrations are not harmonic. What about the harmonic oscillator potential? It will be like this, right, it will not be having this kind of asymmetry. That is the reason why it is called unharmonic potential. In a solid, the potential experienced by an atom is not a harmonic oscillator potential, but it is a unharmonic potential. Now, supposing the potential experienced by the atom is harmonic, what will happen? The potential experienced by the oscillator is, if it is harmonic, then thermal expansion will become 0. This is a very important point. So, atoms vibrating in solids are really unharmonic, right, they are not harmonic, right. So, the potential curve is asymmetric, right. If the atoms are treated as harmonic oscillators, to first approximation you can treat it as a harmonic oscillator, right. The atom which is vibrating can be treated as a harmonic oscillator, but reality the vibrations are unharmonic. So, if you treat the atom to be experiencing a harmonic oscillator potential, then the shape of the curve will be, it will be like this, right, the anharmonic part will be absent, it will become, it will go like this. So, the mean position will be the same, it will remain the same, right, it will not be deviating towards the right, the mean position will not be, this is the mean, right, for this total distance this is the mean, for this distance is the mean. So, it will not go towards the right, so it will go vertically up. That means, when you increase the temperature, in spite of the fact that you increase the temperature, the solid refuses to expand. So, it is clearly stated, it should be understood that if the potential experience of the atom were harmonic, then there will be no thermal expansion. Thermal expansion can be explained only by assuming or by taking into account the anharmonic terms in the potential energy experienced by the atom. So, the potential energy of the atom in the solid is not simply half k x square as you have assumed in the harmonic oscillator problem. You write, what do you, how do you write? You write the F is equal to k x. What is k? The spring constant, that is the Hooke's law. You write force is proportional to strain. So, F is proportional to x, F is equal to k x, it is called a k is called a spring constant. Now, the potential will be equal to half k x square, right. Okay. Integral of f k x is the okay, that is the potential energy. So, when you talk of anharmonic potential, additional higher order terms ought to be included, that should be understood, then only you will be having the anharmonic part, right. Only if the anharmonic part is present, the thermal expansion can be explained. The point I want to stress again is, the depth of the well dictates the bond strength. If the well is shallow, it is weakly bonded solid, it is like aluminum. In comparison with a metal like tungsten, wherein the bonding is stronger because the potential is deeper, right. So, the potential well, the magnitude of potential well, if it is deeper, the binding is stronger. I think I will come back to this again when I deal with the van der Waals bonding, where I will show the thing will be much shallow. The potential curve will be much shallow, indicating that the it is a secondary bond. What is secondary bond? It is a weak bonding, right. Secondary bonding is a weaker bonding compared to the primary bonding, namely the ionic, covalent, metallic bonding, right. Okay. And now, this much will be sufficient with regard to thermal expansion bonding. The correlation between expansion coefficient and melting point. So, I am just showing there is a correlation between the melting point and the thermal expansion. From what I have told you so far, you should have understood by now the meaning of the potential energy curve, right. The shape of the potential energy curve and its dependence and its relation with respect to the strength of the bonding or the melting point. There is a correlation between the thermal expansion or the expansion coefficient and the melting point. Now, look at the materials aluminum, copper, iron and tungsten. I told you enough about tungsten, and also all of you know that the melting point of tungsten is the highest among the solids mentioned now, right. Namely aluminum, copper, iron and tungsten. The melting point of tungsten is 3000 degrees centigrade as against 659 degrees centigrade possessed by aluminum. Okay. What do you observe here? The coefficient of linear expansion when measured at 20 degrees centigrade, this is 23 into 10 to the minus 6 per degree centigrade. For every 1 degree centigrade increase, the expansion will be of the order of 23. Now, when you go from aluminum to tungsten, what do you observe with regard to alpha? The alpha value keeps on decreasing 23 to 17, 11.1, 4.5, right. Then the melting point keeps on increasing. That means, as the melting point increases, the thermal expansion decreases. Why should it decrease? Because in diamond or in tungsten, the bonding is stronger, right. That why you are using tungsten as the filament in a bulb? Thomas Alva Edison found that tungsten to be the best material to be used in a filament, because the melting point of the tungsten filament is much larger. That is the reason why you use tungsten as a filament in a bulb. The melting point is high. The melting point is high means the bonding is stronger, right. Bonding is stronger means what? It is difficult to expand. You have assume a spring, right, to be present between the atoms. So, the bonding is much stronger. So, when you heat it, the expansion will be smaller. When you supposing you take a soft solid like cesium, it is a liquid, almost a liquid metal, or you take aluminum, then the bonding is weaker, then the expansion will be easier, right. The bonding, it is something like a spring. The spring can be compressed or the spring can be elongated. So, the spring is weak, the spring constant is weak, then the elongation will be easier, right. Lower the melting point, the thermal expansion will be larger, right. So, they are inversely proportional, right. So, look at the correlation between alpha and the melting point. So, the lower the melting point, the expansion coefficient will be larger, right. It has got a higher value 3000. So, it has got a lower value 4.5, is that right. So, the thermal expansion coefficient and the melting point are inversely related. That is a message that I want to convey to you, and it indirectly means that the shape of the potential energy curve is important. That is the well depth and also the asymmetric nature. I showed you just now the asymmetric nature, it is sharp like this, right. So, the thermal expansion will be much lesser. In a solid like this, where the potential energy curve goes, the tail is going longer like this, in this fashion, the expansion will be much larger, right. This is for aluminum and this is for tungsten, right. The deeper the potential well, the melting point is higher, and again the thermal expansion will be smaller, right, because the distance that separates this atom and this, that is the movement of the atom, the mean position of the atom, it is much smaller in this case, whereas the mean position it deviates much larger in the first case, namely aluminum. So, there are some other things which are to be understood with regard to the thermal expansion. Primarily thermal expansion is important in metals, right, the ceramics and other materials do not show much thermal expansion, it is not of very great significance. Now, we will move on to the secondary bonding. Why it is called secondary bonding? Because it is secondary, that means the binding energy is much smaller compared to the primary bonding, and the secondary bonding occurs primarily because of the fact that the atoms acquire a dipole moment. The atoms or molecules acquire a dipole moment, and the dipole interactions occur between induced dipole. You can have a molecule, you can induce a dipole moment, you can make the atom should be neutral, a molecule also should be neutral, but temporarily because of thermal fluctuation the atom or molecule which is normally said to be neutral, it can acquire a dipole moment. What is a dipole moment? The positive and negative charge centers will be separated and it will become a electrical dipole, right. So, a dipole moment can be induced in a molecule, induced dipoles. Again the dipole interactions occur between induced dipoles or induced dipoles and polar molecule. What is a polar molecule? A polar molecule is one which has got a permanent dipole moment. I told you that a dipole moment can be induced temporarily, but there are certain molecules because of the asymmetric electronic charge density distribution, they become permanent dipoles, they acquire a permanent dipole moment. So, those molecules are called polar molecules. So, then you can have dipole interactions between polar molecules themselves, right. In one case between induced dipoles, the other case induced dipoles and polar molecules, the third case will be between the polar molecule. They have got one polar molecule which has got a permanent electric moment, another polar molecule which has got again a permanent electric moment. Then between these two dipole interactions can be there, right. Something like a magnetic dipole, you have got a electrical dipoles. Now, we are talking about electrical dipoles, the dipole interaction may be there. Hydrogen bonding comes as one of the special cases in the secondary bonding mechanism, so called hydrogen bonding. By the term hydrogen bonding, one should understand that a hydrogen atom should be involved. So, it may be HCl, right, HCl between another HCl molecule, you can have HCl molecule, another HCl molecule, there will be between the two hydrogen chloride molecules, there will be the weak the secondary bonding will be there, that will be so called hydrogen bonding. One of the atoms should be having, one of the molecule, one of the species should be having a hydrogen atom. Let us look at the secondary bonding in a greater detail. It arises from the interaction between dipoles, right. So, it arises from the interaction between the dipoles. The first case you can have fluctuating dipoles. What do you mean by fluctuating dipole? Temporarily because of thermal agitation, because of the heat given to the material, it is at a higher temperature. Now, what will happen is the electron cloud may become asymmetric, the asymmetric electron clouds. In a hydrogen atom you have got a proton and the electron. You do not consider electron as a particle, it has got a cloud, right. Now, the electron will be assumed to revolve in a circular orbit, or the electron cloud will be spherically symmetric. It will be a sphere and the positive charge center and negative charge center, both of them will coincide, thereby the atom will be neutral. but in some cases there may be fluctuation, right. Due to temperature, what will happen is there may be a fluctuation, thereby what happens is the positive charge center and negative charge centers, they are separated, the electron cloud becomes oblate, it is not spherical. Now, therefore, it becomes a dipole. You see the plus and minus are separated, that means the positive charge center and the negative charge center, they are separated. If it is separated, what happens? It becomes a dipole. What is a magnetic dipole? You have got a north pole here in a magnet, north pole, south pole, it has got a magnet, it is a magnetic dipole. Similarly, here the positive charge center separated from the negative charge center, it becomes a electrical dipole, and then this again becomes another electrical dipole. This atom which is neutral acquires a fluctuating, becomes a fluctuating dipole. So, it becomes a dipole. Now, what do you observe now? The negative sign looks at the positive sign, right, the positive charge here and the negative charge here, they look at each other. So, that leads to bonding, right. Negative will attract the negative, obviously will attract the positive. So, the secondary bonding occurs, right, the secondary bonding occurs here. Now, the example is liquid hydrogen, right. You have liquid hydrogen used in a rocket as a fuel. So, liquid hydrogen, you got the hydrogen molecule here, right, you got a hydrogen molecule and hydrogen molecule here. So, what is the bonding in a hydrogen molecule? What is the bonding? Tell me what is the bonding in a hydrogen molecule? When two hydrogen atoms are combined, you get a hydrogen molecule. As I told you in one of the earlier lecture, the bonding is the covalent bonding. The simplest example of covalent bonding is the hydrogen molecule. So, you should remember in the within the hydrogen molecule there will be the bonding is covalent, but between two hydrogen molecules, the fact that when you combine number of hydrogen molecules and take them to a very low temperature, you have got a liquid hydrogen or liquid helium, then the bonding will be there, right. Otherwise, it will liquefaction will not be there. The fact that liquids exist, that means there is a bonding, right. So, the secondary bonding will be there operating between this hydrogen molecule and another hydrogen molecule. This is called this is obviously leading to giving rise to liquid hydrogen, right, liquid hydrogen. Then you go to, instead of fluctuating dipoles, you go to permanent dipoles, right. They may be the permanent dipoles, or you see here the case of hydrogen chloride HCl, right. You can take any general case, the positive will be here, the negative will be here, right, and this one looks at the negative, looks at the positive, right, the secondary bonding, right. So, the negative looks at the positive. So, if you have one molecule here, another molecule here, when they come closer to each other, if the negative of the region, the negative charge region looks at the positive charge region, then there should be attraction, right. The example will be liquid hydrogen chloride. You have got hydrogen here having proton and electron, chlorine is here, here it will be more negatively charged, right. It looks at the proton here, right. Hydrogen means what? Yeah, proton and electron. So, it will look at the proton, the negatively charged, there are 7 electrons the outermost shell, these 7 electrons will look at the proton. Therefore, the secondary bonding that occurs between the chlorine and hydrogen will give rise to what is called it is a permanent dipole, right, it is a permanent dipole, it is another permanent dipole. So, you got a permanent dipole interaction, that again is secondary bonding. Example is polymer, secondary bonding will be there in the polymer is an example. Let us look at the fluctuating dipole bonds. Weak electric dipole bonding can take place among atoms due to an instantaneous asymmetrical distribution of electron densities around the nuclei. That is what I told you here. The temporary phenomenon, because of thermal agitation, there will be temporary distortion in the electron cloud, or asymmetric electron clouds will be there, that becomes a dipole, right, they fluctuate. So, asymmetrical distribution of electron densities around the nuclei. This type of bonding is termed as fluctuation, right. since the electron density is continuously changing because of thermal motion of the atoms. Because the temperature, the asymmetry occurs because of temperature, right, that should be understood, right. That is the fluctuating dipole moments. A permanent dipole moment or permanent dipole bonds, weak intermolecular bonds which are formed between molecules which possess permanent dipoles. As I told you, now this got a permanent dipole, right. This is a permanent dipole, this is also a permanent dipole. Permanent dipole interaction giving rise to again a secondary bonding, right. Okay. A permanent dipole, a dipole is formed in a molecule if there is asymmetry in its electron density distribution. How will you explain a molecule acquiring a dipole moment? A molecule should be, atom is neutral, hydrogen atom is neutral. Similarly, every molecule should be in principle should be neutral due to some sort of asymmetric electron density distribution. There will be, the molecule will acquire a electric moment. Because of that, you will be having the secondary bonding. And let us now pass on to the summary session. Secondary bonding is present in all the systems and in many liquids and solids, but the magnitude of this is very small. It is something like in magnetism you come across diamagnetism, it is often forgotten. Iron is a ferromagnet, even in iron there will be some amount of diamagnetism. Diamagnetism is omnipresent. Similarly, when you talk of polarization in solids, you talk of electronic polarization, which is again omnipresent, but the magnitude is small and so it is ignored. Similarly, here the secondary bonding will be very weak, right, or the van der Waals bonding is a weak bonding that will be often ignored. It will be present in many systems, right. Similar to diamagnetism or electronic polarization, in magnetic or dielectric materials, the secondary bonding will be present in almost all the systems, but it is often forgotten or it is obscured by the predominant primary bondings, right. Then we will pass on to the question session. How do you explain thermal expansion in the case of metals? What is secondary bonding? Differentiate between fluctuating dipole and permanent dipole. With this we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.